just solved by hand, and this is essentially the same answer in the same way that we solved it. Maybe this gives a little more clarification on something I might have glanced over, but I think I was pretty thorough with that one. So, yeah, if you have any problems, feel free to ask. Thanks. So to wrap this stuff up on LEDs, I just want to give you a little more technical detail, engineering detail about LEDs, and a little bit more of the theory behind them. So if you look at the very top up here, we have an LED, what it looks like, what you'll see in lab, and what you use. You have an anode and you have a cathode. The anode positive, cathode minus. Um, and so what we're going to do there in most LEDs, actually in all LEDs, the longer leg is going to be your anode and the shorter leg is going to be your cathode. And that's the way we tell these apart and which one is which. If you really look inside the LED from the top, from the lens, and you can see in if the top is clear, sometimes you can see this too, but the easier way is to do look at the anode and the cathode and which one is longer. Another interesting way of doing LEDs is you can actually plug these into an ohm meter and measure the resistance going through them. And if the resistance is much higher in one direction and zero in the other, well, you know which way is forward and which way is reverse bias then. So you also know which one is the anode and which one is the cathode as well. So it's another interesting way. So another technical parts of this, you have an epoxy case, which is this blue part. It can be epoxy, plastics, any kind of plastic or whatnot like that. And that does three things. It does, one, it creates a lens which focuses the light and allows it either to focus in one spot or diffuse out nicely in a diffuse pattern. Two, it encases the electronics mechanically so it's harder to break them. Three, it also allows for some of the heat to be conducted easily from the LED itself to the surrounding piece and also to the air around it. And then four, which I didn't really mention before, but four allows essentially air from getting inside of there and air from oxidizing some things and essentially letting water in or water droplets or other things that might have some impact. So protection as well. So if we look right at that LED, right to the bottom right of it, you have the little blue LED with two lines coming off, and that's showing the direction, essentially the circuit symbol for the LED. Now at the very bottom here, we have the emission spectra of LEDs with different materials. So this goes in again to the physics, which is really, really cool, but it's not what we're studying in electrical engineering directly. So I'm going to let you study this on your own. I'll give you some cool YouTubes to learn more if you're interested. But these are different material composites that allow different colors to be made of LEDs and different doping, essentially semiconductor doping. So gallium nitride, gallium phosphide, we have indium gallium, we have gallium aluminum arsenide. Each one of these is responsible for producing different colors of LEDs and different colors of light. And they come down to the physics of how these photons, how much energy these photons have coming off and what their wavelength is. And that all comes down to some really cool semiconductor physics. However, what I want you to know is that the individual materials in that LED, in that semiconductor diode, are what is producing these photons or these different colors. And we can go all the way down to UV, and we can go all the way up to infrared. And the spectrum in between there are the different colors we get. So, interestingly, I know Philips recently has been working on getting a greener green because for the Philips Hue, which is one of their lighting, their lighting products, it's a tunable, Wi-Fi controlled light bulb, which has a whole bunch of different LEDs on it, which allow you to pick whatever color of light coming out that you want. So you can get warm white, you can get cold white, you can get blues, you can get greens, you can get reds, all from the same LED, and it's all by turning on the different settings of RGB LEDs inside of there, and that gives you this tuning. However, for years now, they haven't been sufficiently pleased with the greens, because for whatever reason, green LEDs to get that real true green that they're looking for, which is the kind that they want for their lights, they're not able to get that perfect spectrum yet. So they've been working on that, and actually recently they released a new light bulb this past year, which has a much greener green. The older greens had kind of a yellow tinge to them, and this green, the new green that just came out, has much more of a like a deep Kelly green or a forest green to it, which is kind of cool on its own. And by having that green, that means you can blend better with other colors to get a more full spectrum. And this goes into color science then too, which we actually have a professor who's an expert in color science. If you'd like to chat with, I can hook you up, and you can discuss more of how to mix light to get different colors and to get um, different hues, different shades, and whatnot. But anyway, that's a little bit further than I wanted to go with LEDs. If you want to learn more about this, let me know, and I'll try to post some cool stuff. Thanks, guys.